Hi, this is Mr. Gagnon again, and we're going to talk a little bit about Newton's second law, force equals mass times acceleration. And this is going to relate to your CCA. So first of all, we've got to understand that the amount of force applied to a situation is equal to the mass of the object times the acceleration. Okay, and that's Newton's second law. In this CCA, we're going to be solving for acceleration. So, rearranging the formula, we can divide through the m, and then divide through the m on the other side, and we can end up with acceleration is equal to the force divided by the mass. Okay, so in a situation where you have a car on a track that's pulled by some force, we are able to calculate the acceleration. Okay, so here's a situation, and here's what your CCA is going to relate to. We are going to have a track like this. Okay, it's going to be on the edge of a table, and you've got a pulley here with a string attached to a little car. Okay, and then over the pulley we'll have a hanging mass that's going to be pulling down on the car. So if we put a mass here, this mass will make the car accelerate this way. Okay, there's the basic concept of what we're looking for. So because the car and mass and this mass are part of the same system, we're going to call this M1. We're going to call this M2. So if I were to rewrite the formula for acceleration, I would write it as this. Acceleration equals the force divided by M1 plus M2, because we're looking at a system here. Okay? So because it's part of the system, we've got to include both masses in the system, and the string is not counted in this situation. Although you may think it is, it's really negligible in the effect of the situation. Also, you might be thinking about friction here in the wheels. In this case, we're going to be ignoring that as well. Okay, so we've got force over mass, and the force pulling down is the force that's going to be accelerating this car. And so we've got to figure out how to get this force, and in reality, this force is equal to the weight of this mass. And on Earth, we know the weight is equal to mass times gravity. Okay? So this force pulling down is equal to mass times gravity. So now let's apply some numbers to this. We'll make some simple numbers. We'll say that this mass hanging here is 1 kilogram. We'll say the mass of the car is 2 kilograms. Okay, so hanging mass is 1 kilogram. The car is 2 kilograms. So the force that's pulling down and making the car accelerate is the mass of this times gravity. So if that's 1 kilogram times gravity, okay, the answer for the force here is going to be negative 9.8 newtons. Okay, so that's the force that we found that's pulling on this system. Now, the car yes, you've got a little bit of friction pulling backwards, okay, between the wheel and the track, but we're going to ignore that. Got some friction here between the wheel and the string. You're going to ignore that. And also you've got air friction here between the falling object and the air that's around. We're going to ignore that as well. So the force involved is 9.8 newtons. The masses we can get as well. So if I continue this, okay, I'm going to kind of clean it up a little bit. Okay, so we've got our system, okay, our car system. Okay, we ended up with a mass of 1 kilogram. This mass is 2 kilograms. Make that look a little better. It's not 12, it's 2. And the force pulling down on this, we realized, is 9.8 newtons in the negative direction. So if we apply this to our formula, acceleration equals force over mass, or force over m1 plus m2, we can go ahead and solve for that equation as to what the acceleration should be. So let's go ahead and do that. Acceleration is the force pulling down, which we ended up saying was negative 9.8 newtons, over the mass total, which was, if you add them up, it's 1 plus 2, or 3 kilograms. So if you divide these two out, okay, very simply, 9.8 divided by 3, okay, we end up with 3.3 meters per second squared. And because it is a vector, it's pulling down in the downward direction, that's our acceleration. Okay, and that's the acceleration we're going to get. So this is a typical Atwood problem that is in a car on a solid surface. We're getting a force pulling down, and we're coming up with an acceleration of 3.3 meters per second. Now obviously if you add mass to this, then it's going to accelerate quicker. If you add mass to this, it's going to accelerate slower. So our CCA is going to be to test those two concepts to see really how much it does accelerate more or less in this given situation. Okay, so let's do one problem, a hypothetical, okay, and just to show you what we're going to do. We're going to take a situation where we have a car. Okay, there's a pulley. Okay, and we're going to have a track here. Okay, and let's come up with 3 kilograms for the car, and the mass we're going to have as 2 kilograms. Okay, so here's a situation. Finding the acceleration of this system is going to be as simple as taking the force over the mass total. Okay, which we've got to figure out the forces here. So the force is equal to the weight is equal to mass times gravity. This mass times gravity, so 2 kilograms times negative 9.8 meters per second squared. I'll get you back in the screen here. Okay, so the force pulling down is equal to negative 19.6 newtons. Okay, so we found the force. Okay, not a big deal. That's the force pulling this thing down. So let's go ahead and plug it in. Acceleration of the system is the force, 19.6 newtons, divided by the mass total. Now we've got 3 plus 2, okay, that's 5 kilograms, and we're going to solve for that. Okay, so our answer is negative 3.9 meters per second squared. Okay. Okay, I've got a worksheet to go along with this. I want you guys to practice with a few problems and see if you can achieve the results. I'll put the answers on there for you. And in the CCA that we're going to do, we're actually going to get the actual acceleration of this type of system using an actual cart and finding the actual acceleration. And we're going to come up with a way to test that, and that's through our Vernier software. So again, thank you for listening, and I urge you to rewind this and check back and try to get some of these acceleration problems solved. All right? Have a great day.